Today's topic, systems of linear equations. What does the word system mean here? Well, it means that we don't just have one linear equation, we're going to have a bunch of linear equations. In order to have our best bet for a unique solution to these equations, we'll want to have as many equations as we have unknown variables. So we're going to start here in just 2 dimensions. And in 2 dimensions, we're going to have 2 unknowns, which we're going to call x and y. Those are going to be our variables, or unknowns. And then we need to have 2 equations in order to expect that there's going to be some sort of unique solution to this. Okay, so starting in 2 dimensions is the best for us because we're able to visualize what that means in the x, y coordinate plane here. So here's the x variable and the y variable like that. The 2 equations here means that we're going to have 2 different lines that are defined inside this coordinate system. Okay, so let's say maybe we have one line in the form of y equals mx plus b. I can call it y1 equals m1x plus b1. Where the little subscripts 1 there are to differentiate between the first equation here and another equation, because we need 2 equations with the 2 unknowns. The other equation might look like this, and then we could call that y2, which is m2x plus b2. Okay? Now, if both of these equations are going to be satisfied simultaneously, they need to be obeyed at the same time, there's only really one place in which that happens. Can you guys see that graphically here? That's right, this one intersection point here is the place where both of these equations are obeyed at the same time, so this is what we're going to call the solution. So when you hear me refer to the solution of a system of linear equations, that's the point where the lines intersect. Okay? Now if we're going to talk about 2 lines inside of a plane like this, there's actually 3 different possibilities, 3 different cases that we could be in. And I'll break them down, 1, 2, 3. And the first case is going to be the case that I just illustrated right there, in which we have one unique intersection point. And that means that there's exactly going to be one solution to the equation. Okay? You're guaranteed to have one unique intersection point when you're given 2 equations, as long as the 2 equations have the same slope. Okay, so this over here, this illustrates case 1. Where the 2 lines have different slopes. So you can see that I've referred to these 2 lines in equation format as m1x plus b1, m2x plus b2. So if those 2 things are different, that is to say, referring to this, that m1 and m2 are not the same value. As long as the 2 lines have different slopes, they are guaranteed to intersect in one and only one place in the plane here. Okay, so that's case 1. And the other 2 cases here, cases 2 and 3, both have the fact that both lines have the same slope. Which is to say, referring back to those equations there, m1 is going to be equal to m2. So you can see here, we really have 2 different things. Either the slopes are not equal and we're guaranteed to have a unique solution, or the slopes are equal over here, and then one of 2 different issues can occur. Let's start with case 1 here. The lines are the same. Both lines are in fact the same line. The same exact line. Okay, so I'll just illustrate that real quick with a little picture here. Let's say that I drew my red line like this. Maybe I said my line was equal to y is equal to 3x over here. And then I drew another line just like this, and it was the same exact line, just writing over it. Same exact copy of a line. Okay, if I give you the same line twice, then can you see where the solution would be located here? keeping in mind that the solution means that both of the lines have to be obeyed at the same time. Here, the solution is the entire line. So this is the case that we would call infinitely many solutions. This is the case of infinitely many solutions. But just because there are infinitely many solutions, you can see any single point along this entire line would satisfy both equations at once. It doesn't mean the whole plane, any point in the entire plane is a solution. All the infinitely many solutions lie right on top of the actual line. Okay, so that's what I'm going to call case number 2. And then we have another case, case number 3. And this is still under the part where both of the lines have the same slope. However, either these are both exactly the same line, they also have the same y-intercept, or the lines are just parallel, but not equal. Parallel lines mean that they have the same slope, and by not equal, that means that they don't have the same y-intercept, like here in case number 2. So just to illustrate case number 3, let's say that we have one red line, still the same line going through the origin like that with a given slope, and then we'll have another line which has the same slope but has a different y-intercept. Now these two lines are going to parallel each other. The problem is they have the same exact slope, so they're never going to intersect. This one is going to be exactly that much higher than the other one at all times, so the height difference between them will be the difference in the two y-intercepts. So keeping in mind again that the solution is given by the intersection point, you can see that here, case number 3, there are no solutions at all. This is the only way in 2 dimensions with 2 lines that you're going to get absolutely no solution. Okay, so let's just go over these cases one more time. Case number 1, we have one unique intersection point, also known as the unique solution. That's probably the case that we'd like to be in. Case number 2, well, everything's a solution, so it doesn't really help in decision-making cases. In case number 3, there's absolutely no solution at all. So these 2 cases where the slopes have the same line are things that you generally, in terms of mathematical modeling, would like to avoid. Case number 1 is the one that we're going to look at for the most part. Okay? So we've reviewed here graphically how to recognize a system of linear equations in 2 dimensions and where to find the solution just by eye here graphically. And now we're going to go into some methods of how to find the solution analytically or algebraically. And there's going to be 2 different methods. In general, you can use whichever method works best for you when you're trying to algebraically locate the solution to a system of linear equations. We have 2 methods. The first one I'm going to call substitution, and the other one's going to be called elimination. Substitution. And in the method of substitution here, what you're going to want to do is you're going to have 2 different equations. You take one of the equations and solve it for one of the variables in terms of the other, and then you take that information and plug it back into the other equation. Okay, so I'll start us out with an example here. Let's say that we have this equation obeyed, and at the same time, this equation is also obeyed. If I wanted to solve for the unique solution algebraically, what I would want to do is write one variable in terms of the other. And it doesn't really matter which one you choose, you just choose the one that's working better for you. Okay. In this case over here, maybe I'd like to solve y in terms of x. I'll just take the y and bring it over to the other side. And then I'll take this 2 over here and bring it over to the other side here. So I get the statement that y is equal to 2x minus 2. Okay, so in the method of substitution, the first step here is that you're going to write one variable in terms of the other. And then the next step is you're going to plug in to the other equation. And then you're going to solve that out. Okay, now I have the statement that y is equal to 2x minus 2. So taking that into the other equation, the one that I didn't use for the solving out, I would say that 3x plus 4, and there's the y. Now I don't want the y to be there anymore because I just want to have one equation with one unknown. So I'm going to replace it with this. Don't forget to use parentheses when you're doing that because you can see you're going to have a constant that you're going to have to factor through here. That's still equal to 8, and then I'm going to start to simplify it down. 3x plus 8x minus 8 is equal to 8. I'll bring these over to the other side, and I'll combine these two like terms here, and that'll give me 11x is equal to 16, and therefore x is equal to 16 over 11. So you can see what happened in the method of substitution. After I substituted it in, I had one equation with one unknown, and that's going to give you one unique value for the solution. Keep in mind that this is just a value for x, though. We don't have a statement of the solution that's proper, which would be values for x and y. So now I have to take this answer that I got for x here, and I have to plug it back in somewhere in order to derive a value for y. You could plug it back into here, or you could plug it back into this equation. It doesn't matter because both equations are going to be satisfied at the same time. Okay, so I'll just choose this easier one, that y from up here is equal to 2 times x minus 2, and through simplification you should come up with the value that y is equal to 10 over 11. That's the y value there. So I could either answer as x equals this and y equals that, or I could answer in the point format, and remember in point format the x always comes first and the y comes second. So here's the format as an x comma y point, 16 11ths, 10 11ths. Now if you have a graphing calculator, you'll want to go ahead and confirm that answer by taking these two equations here, solving them both for statements of y, and graphing them at the same time on your graphing calculator. Then if you zoom in using the window function or the zoom function, you should see those lines intersect right at that point, and that's a good check to make sure that you're on the right track. The other thing that you can do that will definitely check your work for you is you can take the x value and the y value, and you must plug it back into both of the equations to make sure that they both hold true. Okay, so let me say that again. This is a type of problem where you can always check your work and confirm whether or not you've got the right answer, but make sure that when you plug in these values that you don't mix up the x and the y. And also make sure that when you're checking your work that both of these equations are confirmed to be satisfied. You don't want to just plug it into one of them and then get that and say, oh yeah, I got the answer. You have to make sure that you've plugged into both of them and that both those equations hold true. So those are two different ways that you can check your work when solving this out. Okay. So that outlines the method of substitution, and now we're going to go over an alternative method known as the method of elimination. And usually you can just pick whichever method you prefer. They both get you to the same place, and if you have time you might want to even try them both. So the other method, method number 2, is called elimination. And let's see, I'll get another example for us here. Let's say we have the system 4x plus 6y equals 8, and also 2x minus 4y is equal to 18. Again, you can see we've got two equations with two unknowns here. And what we want to do in the method of elimination is conceptually, we're going to stack these equations. You see I've written them one on top of the other. And we're going to try to eliminate one of the variables by making a match. For example, here we have a 4x, right? If we had a 4x right here, and then we subtracted it away, then we will have eliminated x. Okay? So that's what I'm going to try to do here. And just like you're used to, if you ever have an equation, you can multiply both sides of the equation by any number you want. It's up to you. Don't use the number 0, but any other number, you can just multiply the whole equation by that. So I'm going to choose here to multiply this second equation by the number minus 2. Okay, so let me just rewrite this since this is our first example. This first equation I did nothing to. The second equation I chose to multiply the entire thing by minus 2. So that means I now have a minus 4x there. Here I have minus 2 times minus 4, which is plus 8y here. Here I have minus 2 times 18, so that's a minus 36. And these are the same thing. This is the same problem that I had before. I did not change this equation. I simply did the same thing to both sides. Okay? But now you can see why it's called the method of elimination here, because if I choose to add one equation to the other equation, 4 minus 4x, 4x minus 4x gives me no x's at all. 6y plus 8y, that's going to give me 14y. And then I'm going to have 8 minus 36, and that's going to get me to a negative 28. Okay, I've eliminated the x, and therefore I've gotten down to one equation with one unknown, and you can see that's the same theme for this method over here, is that eventually in part B, we wanted to get down to one equation with one unknown, and we know how to solve that. Okay, so we've got one equation with one unknown here. Dividing by 14 on both sides yields the solution for the y value, which is to say that y is going to be equal to negative 2. Okay? And then just like in the other case here, once we got down to one equation with one unknown, we then got one of the values. Then we had to plug back into either one of the equations, doesn't matter, we get the other value. So here, I've just got the y value. So just keep in mind you're not done with the problem yet. You have to take that y value, plug it back into either one of the equations, and you're going to get the x value. So you can just get the x value here by, let's say, using this first one, 4x plus 6 times minus 2 is equal to 8. Therefore, 4x minus 12 is equal to 8, or 4x is equal to 20, or x is equal to 5. Now I've got the true solution, the unique solution, because these are two lines with two different slopes. The x value will be 5, the y value will be minus 2, or if you'd like to answer as a point, the point will be 5 comma minus 2. And again, I encourage you to check your work each and every time, not only by taking these two values and plugging them back into both equations, but also solving these two things out for y and then graphing them both on your calculator, your graphing calculator, at the same time. You should see those two lines intersect at the point 5 comma minus 2. Change your window on your screen if you're not able to see where the lines intersect, and those are two great ways to check your work each time. Now I'm going to go into a couple examples of this, why we would want to use systems of linear equations. And this happens very commonly, especially if you're trying to run a business. You know, there's not just one single aspect to your business. There's a lot of different choices to be made. And the reason that we study math in business is to help us make the best, most educated decisions possible. Okay, so maybe this would help us with a business example here. Let's say that we're running a tour company. And in our tour company, let's say we have two choices. Right now we're working with a system with two equations, two unknowns. So let's say that we have two tour types. And the basic tour is $20 per person. So the little PP there, is per person. It costs $20 to get on the basic tour. And then let's say that we have a VIP type of tour. That's a little more expensive. Maybe it comes with a dinner and dancing thing. And that's going to be $45 per person. Okay, so we have two different tours. Those will represent our two different variables. And then we have a goal here. The goal for our revenue is to make, let's say, $2,625 from 100 people. Okay? So these are per person rates, and let's say that I can afford with my staffing to give tours all together to 100 people, depending on what tour they pick, doesn't matter. The goal for my revenue is to make $2,625. How many people do I need to get on each tour in order to reach that goal? Okay, so that's the question, is how many people for each tour? In order for me to satisfy that goal, And again, remember that when we're working in a word problem, the very first thing, some of the hardest parts of a word problem, is going to be to just start with the setup. We're going to be learning about systems today, so we're going to have two variables. We're going to have an x variable and a y variable. And I want you guys to really try to think critically about what the setup is. So pause the video here and write down what you think I'm going to write for the values of what x and y will represent. Okay, so what I'm looking for here is, I have a revenue goal. How many people in each tour? How many people is a hint to me that the units on x and y should both be number of people. Doesn't really matter which way you pick it as long as you're consistent. So x I'll say is the number of the people on basic tours, and y is going to be the number of people in the VIP tours. Okay, they're both a number of people. The answers to the question is, how many people do I need? So my unknown is how many people, and so that's your hint to get you started on the problem. Okay, so now you can see from the setup over there that there's a couple things that I have not yet taken into account. I've got my setup here, but I haven't said anything about the pricing or the goal or anything like that. So now I want to make up or create two equations that will allow me to solve for the two unknowns. Okay, so that's all I'm going to say for now. Go ahead and pause the video and try to write down two linear equations that relate x and y that I can then solve for a unique solution. Okay, both of those equations are going to involve the x and y here. The first statement is there's 100 people altogether. That's what my staffing can afford. So the number of basic and the number of VIP people altogether will yield me 100 people. The other one, a little more complex, is going to involve my revenue goal. I have a total revenue goal of $26.25. And that's going to depend on how many people I have in each tour. I make $20 off the basic tour people. I make $45 off each of the VIP tours. And so you can see there's a form of a linear equation which I can now solve out for the unique solution x and y. You can use either one of the methods. You can use elimination, you can use substitution. It's totally up to you. But I'll just go through this one using substitution here, where I will rewrite y in terms of x. So this first equation tells me that y is equal to 100 minus x. And then the second equation here is going to be 20x plus 45. Don't forget about the parentheses because you'll need to factor the 45 through. 45 times 100 minus x is equal to 2625. Okay, so then we have 20x plus 4500 minus 45x is equal to 2625. And then we can combine these two like terms together. Minus 25x here is going to be 2625 minus 4500. I forgot to bring my calculator today, but I hope you brought your calculator, so you're going to crunch this number out. Negative on this side, don't worry about it, because it looks like we're going to get a negative on that side. And the answer that you guys can check, and hopefully you confirm for me, is that I get the solution x is equal to 75. Once again, remember that either method you choose is going to yield you one equation with one unknown, and that just gets you one answer. So in questions like this, we are going to want to answer the full question, how many in each package. So if we have 75 in the basic, we can plug back into this top equation here. 100 minus 75 gives us 25 in the VIP tours. Okay, so the answer to the question is I would want to have 75 people on this tour, 25 people on that tour, and that will get me to hit my revenue goal that I wanted. Of course, if I can persuade a few more people to take the VIP tour, then I'm going to get even more revenue from that. Okay, so that's a really fun example that you might find in business. And then to close it out, I've got one more example for you. And this example is in terms of mixing some solutions together. So let's say that we have two solutions. Maybe it's a drug or some sort of chemical or other type of mix, or maybe we're even baking or something. We've got two different mixes, and we want a certain concentration. How much of each mix should we have? So I wanted to use an example that was in my real life. Right now I'm doing a lot of gardening, and to prevent powdery mildew inside my garden, I've actually been spraying with a pesticide called neem oil. I don't know if you've ever heard of it. It's pretty natural. It's kind of pretty harmless, except to bugs and powdery mildew. So let's say, for example, that I want a 25% solution of my fertilizer, or sorry, it's not a fertilizer, it's a pesticide called neem oil. Okay, and then let's say I have gone to the store and I've seen all the different products available that have it, and I have two products in my home that I've purchased. One is, let's call it solution A, is 10% neem. And let's say that solution B, the extra strength solution, is 40% neem. And then let's say I went on the internet and I looked up how strong of a concentration should I be spraying at a certain time, and it says you shouldn't be doing either one of those. You should be spraying at 25%. But I don't have 25%. I just have the weak one and the strong one, so I'm going to need a little bit of each. Okay, so let's say I want altogether 2 gallons, because I have a 2-gallon pump sprayer of 25% neem. The question is, how much in gallons should I use of product A? How much in gallons should I use of product B? So that's a hint to help you with the setup. So again, let's say we're going to define X and Y. The setup's sometimes the hardest part of a word problem. What do you want the variables to be in words? And then we can move on to setting up the equations. That's right. Each one of these variables here is going to represent a number of gallons of the different products A and B that I'm using in order to reach my goal. So let's say X is the number of gallons of product A, and then Y is going to be the number of gallons of product B. And when I mix it all together, I want to have 2 gallons total. And with all the concentrations in place, I'd like the overall concentration to be 25%. Okay, so again on this board we're going to want to write down with the other information given the 2 equations that we will solve out using one of the methods. Go ahead and pause the video and take a minute to try to write down what you think the setup's going to be. Okay, so let's see. The easier one probably is that the number of gallons of A plus the number of gallons B has to be the total 2 gallons that I want. So that means that X plus Y, that's going to be equal to 2. Hopefully that's the first one you wrote down. That's the easier one. The other one's a little bit harder. What am I supposed to equate here in order to say that I've got 25% neem? Well, I've got 2 gallons of something that's 25% neem. So the other equation that I'm going to have, this one here, is the total amount of liquid in gallons. The other equation involved is going to be the total amount of neem that I have altogether in terms of gallons. Now if you didn't yet get the second equation, why don't you use this hint that the second equation is the total amount of neem, and pause the video and try to write down that equation now. So how much total neem do I have? I have 2 gallons and it's 25% neem, so that tells me that I have, let's say, 2 times 25%, or 0.5 gallons total of neem. That makes sense, right? So it's a 2-gallon container and it's a quarter of it is pure neem, so that means that's half a gallon of that. Okay, so anyone who's actually used neem oil knows that that's a ridiculous amount of pure neem oil. So anyway, let's go into writing down how much we're going to get off of the gallons of both of these concentrations here. Okay, so X, that one is the gallons where we have 10% neem. So remember, percentages, when you're working mathematically, usually you're going to have to turn them into their decimal equivalents. So that's going to be 0.10 times the gallons of X. and the other one's 40%, so that's 0.40, and that's times the gallons of Y, and that's going to equal to 0.5, and you can see the 0.5 I got by saying it's 2 total gallons, and that desired concentration is 25%. Okay, so now we're going to want to be able to solve this out, and you can use either method you want. I encourage you to go ahead and try both of the methods. Let's say that maybe I'll use the other method this time to illustrate that. So I'll just copy these down again. X plus y is 2, and then 0.1x plus 0.4y is 0.5. I'm going to want to multiply one of these equations on both sides by something that just totally eliminates it. Okay, so here I have an x, and here I have a 0.1x. So if I multiply this entire equation over here by the constant minus 10, let's see what happens there. The first one was, again, x plus y is 2. And now we're going to have minus 10 times 0.1, so that's minus x. And then we're going to have minus 4y. And then we're going to have a minus 5 over there. And you can see that if I add these together now, I'm going to eliminate the x variable. That's what I was after. So I've got 0x, and then I've got 1y minus 4. Careful there with the algebra, that's minus 3. And then 2 minus 5, that's minus 3. And so that tells me that y is exactly equal to 1. Okay, so I got it. I got that the number of gallons of solution B I'm going to use is 1 gallon. And how much from x? Well, if I use 1 gallon on y, that means that x, therefore, since x plus y is equal to 2, that means that x must also equal 1. So I'm going to have to take 1 gallon of the x, 1 gallon of the y, mix that together, and I'll get 2 gallons that are at the average concentration. You may note that the average of 10 and 40 is 25%. Okay, so see more examples on the internet, and I hope that you enjoy making use of these linear equations inside your many applications.